This video represents part 3 of our discussion of applications of partial derivatives in thermodynamic systems. We'll take a look at a couple derivatives that represent physical changes that may occur in systems, be they gas, liquid, or solid. The first of these is the expansion coefficient, represented by the symbol beta here. If you take a look at this particular coefficient, you'll note that we have a partial derivative which shows changes in volume with respect to temperature under conditions of constant pressure. Now, constant pressure conditions are frequently referred to as isobaric. We know, of course, that when we increase the temperature, the volume increases. So what that means is that this partial derivative that shows changes in volume with respect to temperature will be greater than 0. The use of the 1 over v here means that this particular coefficient represents a fractional change. So essentially the percentage change in the volume that occurs when we increase the temperature by a certain amount. The next quantity that we're looking at is called the isothermal compressibility, and of course the subscript T here represents that isothermal property. Again, we take a look at our derivative, which represents changes in volume that occur when we change the pressure, essentially the rate of change. And here we'll note that for most systems, when you increase the pressure, of course, you're compressing something, the volume will decrease under isothermal conditions. So that means that this partial derivative will be less than 0. It's going to be negative. And for that reason, we actually attach a negative sign to this particular coefficient so that the overall sign of kappa, the isothermal compressibility, will be greater than 0. So tabulated values that you'll find in various thermodynamic tables will always be positive there. Again, we'll note that we have 1 over v here so that we're dealing with the fractional change that occurs in these particular systems. Now, if we think about an ideal gas, what we can show is that the isothermal the isothermal compressibility kappa for an ideal gas is just simply 1 over P, 1 over the pressure, and the expansion coefficient beta is just 1 over T, which represents the change that occurs when we increase the temperature of the system. We'll run through a quick mathematical proof to show that this is true for an ideal gas. Of course, we start with the basic equation for an ideal gas, that the volume is equal to nRT over P, so that when we're looking to the isothermal compressibility, we'll note that if we take the derivative of that with respect to pressure, we get the nRT, negative nRT over P squared for the derivative of that particular term. Then, of course, if we divide by negative volume, which is the definition of our isothermal compressibility, dividing both sides by that, volume, of course, is nRT over P, so negative volume is negative nRT over P. Taking a look at that, we'll notice that the negative nRTs cancel out, so we're left with 1 over P squared divided by 1 over P, which is the same thing as P over P squared, and of course P over P squared is very simply just 1 over P. So there's the derivation that shows that for an ideal gas, this isothermal compressibility is indeed 1 over P. Now we can do the same thing with regard to the expansion coefficient. Again, taking the derivative of volume with respect to temperature for the ideal gas, we just very simply get n times R over P. Dividing through by P on both sides, we find that, divided through by V on both sides, we find we have this. The nR over P cancels out, and so we're just left with T there in the denominator, and so we end up with a situation where beta is equal to 1 over T. Now we can take a look at how we might apply the expansion coefficient to real systems, and here's a problem associated with thermal expansion of water that might simply accompany a temperature increase of 3 degrees Celsius. Of course, as we talk about things such as global warming, an increase in temperature of 3 degrees Celsius is certainly within the range of those estimated by current models. So we can do what we might call back of the envelope calculation as to how much the sea level might rise simply through expansion of water. We're going to be doing this problem in class, so I'm not going to go through the computational details here, just to kind of lay out the theoretical framework of how we might do this. Of course, liquid water is not an ideal gas, so we cannot use those relationships that we had on the previous slide. We have to kind of go back to the basic equations. So this really gets down to how do we set up a problem when we're trying to determine a change. Well, we'll set it up in differential form this way. What are we trying to figure out here? Well, if we're going to figure out the oceanic depth, the first thing we want to do is we're going to try to figure out the change in volume that occurs when we increase the temperature. So we will always start by saying, okay, I'm interested in a change in volume. So I'm going to write down, because I'm interested in change in volume, I'm just going to simply write down dV. Alright? And so what's that equal to? Well, so what's causing the change in volume? In this case, we're talking about temperature causing the change in volume. So we write down a partial derivative that represents changes in volume that occur when we're changing the temperature. And so we're going to write down change in volume with respect to temperature. And we're doing this under conditions of constant pressure, so we add our subscript. And then we just very simply multiply it by the differential representing that variable which is changing, which of course again in this case is temperature. So this is a basic equation we would write to determine the change in volume. And keep in mind that we would write this for any kind of property that's changing in our system. Again, we start with a differential representing the property that we're trying to calculate, the change that we're trying to calculate, dV. We multiply it by the appropriate derivative, which is the variable, of course, that we're changing is temperature. So we have that partial derivative which shows the change with respect to temperature. And then again, multiplying it by the differential representing the changing variable in the particular system that we're studying. And so what we need then is a representation of that particular partial derivative. And so we know that based on the definition of beta, and just rewriting that definition of beta here, beta was 1 over v dv dt at constant p. And so therefore our partial derivative dv dt at constant p is just very simply equal to beta times v. So we just make that substitution into our equation, and this gives us our second result here that shows that differential with respect to v, dv is equal to beta times v dt. Okay, so now that we've got dv is equal to beta times v dt, we're going to divide, because we've got volume on the right side of the equation. What we need to do is make sure we get in these differentials equations, we need to make sure that we get the similar variables on the same side of the equation. So what we're going to do is we're going to divide through by volume, and that's going to give us this expression here, dv over v equals beta times dt. And then of course, what do we need to do to get the change in volume? In this circumstance, the answer is integrate, which is of course our standard answer to the vast majority of questions that we have in this course. Now, of course, again, for an ideal gas, we showed that we could derive an expression for beta, but we're dealing with not even a gas here, we're dealing with a liquid. So we'll have to refer to thermodynamic tables to get values of beta. And we will assume this to be independent of temperature. That's not entirely true. The expansion coefficient does in fact depend on temperature, but we will assume it to be independent of temperature. So we go to our thermodynamic tables and we get a value of beta as indicated in the problem itself. It's 2.04 times 10 to the minus 4 inverse Kelvin up here at the top in the problem. This is the particular value they're going to use in our calculation. But the key here is we are going to assume it's a constant, and that means that we integrate, that's going to come outside the integral, so we integrate both sides of the equation and we get this expression, the natural log of the final volume over the initial volume is equal to beta times the change in temperature that occurs. And in this case, of course, that change in temperature is equal to -3 degrees. So we will use this expression to calculate our result in class. Now you may recall from our previous video, at least I certainly hope you recall, that we talked about changes in internal energy that occur during an isothermal process when we change the volume, and we said for an ideal gas that was equal to 0. Again, the partial derivative that was key there was the internal pressure. And again, for an ideal gas, we showed that was equal to 0. In this particular problem, what we're going to show is that the internal energy doesn't change when the pressure changes. Again, isothermally. Now, you may recall from our discussions earlier that if there's an isothermal change in the system for an ideal gas, because there are no interactions, we do not expect the internal energy to change. But here we're going to improve that mathematically. If we know that the internal pressure du dV at constant T is equal to 0, can we show that the same would be true for a pressure change? So we're going to start again by setting up our differential here and what we're trying to show. And again, as we noted before, we're interested in changes in internal energy, so that's du when we change the pressure. So we write a partial derivative that shows du dP isothermally, meaning that there's a constant temperature, and we multiply it by dP, the pressure that we're changing. If we go back to the fundamental equations that we talked about earlier in earlier videos for changes in internal energy with respect to volume, we can go back to that, and of course, again, what we learned from that was that du was equal to the internal pressure pi sub T times dV plus Cv dt, Cv being the constant volume heat capacity. So to get du dP at constant T, we're actually can treat this more or less algebraically. What we're going to do is we're going to take this basic equation and divide through by dP, so that on the left we get du dP. And then we divide through by dP. We're going to end up with dV dP, and we're going to end up with dt dP here when we divide through by dP. So we're actually generating some additional partial derivatives as a result. So that gives us this equation here, where we now have an expression. And additionally, what we'll note here is that, as we did before, we end up with this expression where we divide through by dP. The other thing that's important to note is we also have to add the condition that this is isothermal, so the partial derivatives must reflect that the temperature is held constant, so that we have the subscript T associated with each of the partial derivatives. Now, if we go ahead then and recognize for an ideal gas that the internal pressure is equal to 0, we can eliminate that first term from the expression, and that leaves us with this second term here, and for some reason part of the partial derivative didn't show up, so we're just completing that. But we have the second term. So now we have this expression that du dp at constant T is equal to constant volume heat capacity times this derivative of temperature with respect to pressure at constant T. Now let's take a look at that and think about it. What is this equal to? dt dp at constant T. Well, it's an isothermal process. The temperature is constant. And what that means is that dt is equal to 0 because it's isothermal, the temperature is constant, and therefore that partial derivative is equal to 0. And if that partial derivative is equal to 0, that means du dp at constant T is also equal to 0, which is what we were trying to prove. Again, this is what we expect because, as we said, for any isothermal process involving an ideal gas, there should be no change in internal energy. And therefore, these partial derivatives, which represent constant temperature processes, must be equal to 0. This ends part 3 of our discussion of partial derivatives in thermodynamic systems. We'll have one more video. We'll take a look at some additional situations involving partial derivatives that will be posted shortly.